Hello, dear friends. This is a lecture of fracture mechanics. The content of the course is material science and engineering. I am going to give a brief lecture on this topic. Uh, the content of lecture contains brittle fracture, criteria for fracture, ductile to brittle transition. And most of the lecture materials are taken from these books: Fracture Mechanics book by T.L. Anderson and Fracture Mechanics by C.T. Dodson and Z.H. Jan. So for the beginning, I'll start from the theoretical fracture strengths and the crack ideas. So for that, let's consider a perfectly crystalline material loaded in tension. The failure by fracture, sorry, let me take this into, okay. So failure by fracture occurs if the bonds are broken and the fresh surfaces are created. Okay. So if two atomic planes are to be separated, the force required initially increase to maximum F max and then decrease. So the maximum stress corresponding to F max is the theoretical strength sigma T. This stress is given by formula sigma TFS, which indicates theoretical fracture strength, which is equals to sigma T, which is theoretical strength, which is uh, approximately equal to E gamma over A naught. So on this E implies the Young's modulus of material, gamma implies the surface energy, A naught equivalent equilibrium distance between atomic centers. That means atomic distance. Okay, so for by atomic approach, we can represent the theoretical fracture strength sigma TFS approximately E over 2 pi. That is by atomic approach. This implies that the theoretical fracture strength is in the range of Young's modulus over 10 to Young's modulus over 6. The strength of real material is of the order of E over 100 to E over 1000, which is much lower in magnitude. Teeny crack are responsible for this. So this statement can be shown here. This y-axis implies amplitude of force F, and the x-axis implies the atomic radius or atomic distance. Okay, so this is the graph increasing on up to F max and then decrease then. So the point here indicates that the maximum equilibrium distance between atomic centers. Okay, so this is equilibrium point. So for aluminium, these are the material properties. The youngest modulus of aluminium is 70.5 gigapascal. The atomic distance, atomic center distance or equilibrium distance is 2.86 angstrom, and the surface energy is 0.704 Newton per meter, and the theoretical fracture strength sigma T, or the theoretical strength T, which is equal to 13.16 gigapascal. This is for particular aluminum material. Again, that crack plays the same role in the fracture of a weakening as dislocation play for plastic deformation. Fracture. So fracture is related to propagation of cracks. When crack propagates, it leads to a fracture, and it also leads to the failure of material or components. If there are no pre-existing crack, then the crack needs to nucleate before propagation. that propagation is for the going for the failure point, and nucleation is the initiation of crack. So crack nucleation typically requires higher stress levels than crack propagation, because once the damage initiates, then the propagation will need less energy. A crack is typically a sharp void in material, which act like a stress concentration or a stress amplifier. Hence, crack is an amplifier of far-field means stress. Okay, so cracks themselves do not produce stress, but crack amplifies the stress. Cracks in general may have several geometries. Okay, even in a circular hole can be considered as a blunt crack. Okay, if it is a perfect circle, it is a blunt crack, and the crack may lie fully enclosed by the material or may have a crack face connected to the outer surface. Okay, so cracks connected with outer surface may be profoundly influenced by the environment, because many environmental factors are there: the moisture, the heat, and the corrosion. Okay, that exposed to atmospheric situation. Crack propagation leads to the creation of new surface area, which further leads to the increase in the surface energy of the solid. However, in a fracture, the surface energy involved is typically greater than the intrinsic surface energy, as a fracture involves in subsurface atoms to some extent. Additionally, the fracture surface energy may involve terms arising out of energy dissipation due to microcracking and phase transformation and plastic deformation. So here we can see this is a crack in material. The size of crack is given 2A, and the fracture surface energy gamma F, which is greater than intrinsic surface energy gamma for the crack to be initiated. Regions of stress concentrations help in the process. Fracture mechanics is the subject of study where in the material resistance to fracture is characterized. In other words, the tolerance of materials to crack propagation is analyzed. Crack propagation be steady, means that is a slow increasing crack length with time or with load, or can be catastrophic. That means unsteady crack propagation leading to a sudden failure of material. So what dislocation is to slip, crack is to fracture. This means under tensile loading, if the stress exceeds the yield strength, the material begins to plastically deform. The area under stress strain diagram in the tensile testing is designated as the toughness in uniaxial tension. Toughness relates to the energy absorbed to the fracture. Similarly, in the presence of crack, we arrive at material parameter which characterize the toughness of the material in the presence of crack. That is the fracture toughness. In most materials, even the material is microscopically brittle. That shows very little plastic deformation in uniaxial test. There might be some difficulty at the microscopic level. This implies that in most materials, the crack tip is not infinitely sharp, but it is sometimes blunt, and a little blunting occurs by plastic deformation. This further avoids the stress singularity at the crack tip, as well as we shall see it later. So here we can see a sharp crack tip. Here there is no blunt on the crack. and this is a blunting process. So these sharp corners are considered as stress risers. Okay. So one of the important goals of material or component design is to avoid catastrophic failure. If the crack propagation is steady, then we can practice preventing maintenance. That means replacing the component after certain hour of service. This can be done in the case of catastrophic failure. The subject of fracture mechanics has its origin in the failure of worldwide second Liberty ships. In one of the cases, the ship virtually broken into two with a loud sound when it was in the harbor. That is not in fighting mode. This was caused by the lack of fracture toughness at the weld joint, resulting in the propagation of brittle cracks. The full list of fracture distribution to this failure is as shown in the figure. So breaking of the Liberty ship is there. The reasons are the welding instead of repeating is one of the case, and the existence of cold water. Again, high sulfur in the steel. These are some of the factors for the breaking of the ships. Okay, another, when we come to welding, continuity of the structure is one of the factor. Residual stress developed while welding is another, and the micro cracks in the welded joint. Okay, so this is it is seen that welding was done for faster production, but this results in micro cracks and residual stress are developed, which leads to brittle crack propagation. This problem becomes global as this provide continuity of crack paths across plates. So instead of one plate breaking, the entire ship broke. High sulfur in steel contributed to the brittleness of the plates. Due to the cold seawater, the ships were harbored and the hull material under one phenomena known as ductile to brittle transition. Okay, so ironically, this days of the ship leads to the birth of the fracture mechanics as a systematic field of study. What is crack? That is a question. So, as we have seen, crack is an amplifier of a far field stress. The sharper the crack tip, the higher will be the stresses at the crack tip. It is a region where atoms are debonded and an internal surface exists. This internal surface may be connected to the external surface. Cracks can be sharp in brittle material, while in ductile material, plastic deformation at the crack tip blunts the crack, leading to lower distress at the crack tip and further alteration of the nature of the stress distribution. Even a void or a through hole in the material can be considered as a crack. Okay. So a second phase, usually hard brittle phase. Actually, second phase in the material is the matrix phase. Okay, there are fiber phase and the matrix phase in the case of composite. So, and in a needle-like geometry can lead to stress amplification and hence be considered a crack. Further, debonding at the interface between the second phase and the matrix can lead to formation of interface crack. Sorry, the second phase is the fiber phase. As the crack propagates, fresh or internal surface area is created. The fracture surface energy required for this comes for the strain energy stored in the material, which could further come from the work done by externally applied load. In ductile material, energy is also extended for plastic deformation at the crack tip. A crack reduces the stiffness of the material or the structure. So this is a crack size 2A, and crack is a local stress amplifier since rather than a global weakener by decreasing the load bearing area or the load bearing capacity of the structure. Characteristics of crack. Cracks can be characterized looking into the following aspects. It connects with the external free surface, uh, completely internal. Internal cracks which connects to outer surface, and surface cracks. So crack with some contact with external surface are exposed to outer media and hence may prone to oxidation and corrosion. So crack lengths, the deleterious effect of the crack further depend on the type of crack. That crack first, second, or third, as shown here, completely internal crack with connection to the outer surface, or surface crack. Okay, crack tip radius. This the shaper or the sharper the crack, the more deleterious it is. Crack tip radius is dependent of the type of loading and the ductility of the material. And the third one is the crack orientation. With respect to the geometry and the loading, we will see more modes of the loading in the this context soon. Okay, actually this is the crack length, and crack tip radius is here. The radius is here. Okay, this is the crack situation. Mode of the formation of cracked body, or modes of fracture we can call. In general, we have three modes of loading of cracked body can be considered, which are called the modes of deformation, or that is the first mode, second mode, and the third mode. The first mode is called opening mode. Okay, it is opening mode. The second mode is sliding mode. We can easily see from the picture. This is opening. It makes the crack to open this and this side. Or we can see this and this side. Then the crack will open. In this case, sliding mode. This pushes this direction and this pulls in this direction. So the two materials will slide to each other. And here it makes kind of tearing or scissor effect. This is a scissor effect. So that is third mode. In the general case, for the crack in an arbitrary shaped body under an arbitrary loading, the mode is not pure. It is mixed mode will be there. Okay. So modes of deformation are given like this. Okay. The loading specified and the geometry of the specimen illustrated for mode 2 and 3 above do not give rise to pure mode 2 and the pure mode 3 deformation. Others constraints or body shapes are required. Important points in fracture. One of the goals of fracture mechanics is to derive the material property, the fracture toughness, which can characterize the mechanical behavior of the material with flaws or cracks in it. Fracture can broadly be classified into brittle and ductile fracture. This is usually done using in the macroscopic ductility observed and usually not taking into account the microscopically plasticity, which should be significant. So ductile materials is one which yields before fracture. Further, one would like to avoid the brittle fracture, wherein the crack propagation leading to failure occur with very little absorption of energy. In brittle fracture, the crack may grow unstable without much predictability. Three factors uh, have a profound influence on the nature of fracture. One is temperature, second is the strain rate, and the third one is the state of stress. Okay, so materials which behave a brittle fashion at low temperature may become ductile at high temperature. When a strain rate is increased by a few order of magnitude, a ductility of material, ductile material may start to behave in a brittle fashion. So that is the three factors, the correlation. So uh, ductile material sigma yield is less than to sigma of failure. Okay, so fracture, ductile and brittle, that is classified into two, and the brittle fracture promoted by the three factors uh, that profound the influence of nature of fracture. These are low temperature, high strain rate, uh, triaxial state of stress, this brittle fracture profound by. Again, fracture affecting factors affecting fracture, this temperature, strain rate, and state of stress, which is specified here. High strain rate and low temperature essentially have similar effect of not allowing thermally activated motion of dislocations. That is not helping plastic deformation by sleep. And in specific case, some of the sleep systems being active at high temperature may become inactive at low temperature. Okay. So by triaxial state of stress, we mean tensile stress of the same sign along Y and Z also. And the triaxial state of stress does not promote crack propagation, but suppress the plastic deformation. Since the plastic deformation is suppressed, the crack tip remains sharp, this promoting brittle fracture. So far, for the plastic deformation, the following orders is better. Triaxial is less important than biaxial, and the biaxial is less important than uniaxial. So the uniaxial is the best one. Okay, this is triaxial. Stress in X, Y, and Z. Stress in X and Y, and the stress in X, or we can call it as it is local orientation, sigma 1, sigma 2, and sigma 3 for triaxial case. For biaxial case, sigma 1 and sigma 2. And in the uniaxial case, sigma 1 is so the worst scenario in the triaxial case and the best scenario to avoid brittle fracture, uniaxial test is preferable. Fractography. Considerable amount of information can be gathered regarding the origin and nature of fracture by studying the fracture surface. In fatigue failure, for instance, we can know the place of origin of the crack, stable crack propagation regions, etc. The fracture surface has to be maintained in the pristine material that, and the oxidation, contact damage, etc. should be avoided to get meaningful information from fractography. It should be noted that a sample which shows very little macroscopic ductility may display microscopic ductility. as can be seen in the fractograph. We can see here a result of fractography. So a truly brittle sample shows faceted cleavage planes. We have cleavage planes here. Okay, these are the faceted cleavage planes. Okay, while ductile fracture surface display a dimpled appearance. Okay, so a scanning electron microscope, fracture surface by scanning electron microscope can be shown in this picture. Classification of fracture. Okay, fracture can be classified based on the crystallographic mode, appearance of the fracture surface, strain to fracture, and crack pass, and also other factors also there. Okay, so presence of chemical species at the crack tip can lead to produce fracture stress and enhance crack propagation. Presence of brittle phase along the grain boundaries. Okay, for Fe3C along grain boundary in steel, glassy phase at the grain boundary in Si3N4 ceramics can lead to intergranular crack propagation. This preferred weak pass along grain boundaries implies low energy expenditure during the fracture, that is low fracture toughness. So we can see here there is a transition. These are grain 1 and grain 2 is there. There is also a transition here. Okay, so this is the weak pass along grain boundary. Okay, and there are brittle cementite along grain boundary along the which crack can propagate are presented here. Okay. So the behavior described and term. So crystallographic mode, we can see shear mode and cleavage mode. If that shear mode or ductile and cleavage mode or brittle, appearance of fracture surface, fibrous and granular or bright, strain to fracture, that is ductile and brittle, phase, transgranular, that is crack propagates through the grains, and intergranular phase, that is crack propagates through the grain boundaries. Okay, so these are type of failure in uniaxial tensile tension or tension tests. One is the cleavage plane. So for the brittle fracture, little or no deformation observing a single crystals and polycrystalline have been observed in the BCC and HCP metals, but not in FCC metals. Here we can see the slip plane, that is shear mode. Here the fracture is a shear type of fracture failure. So shear fracture of ductile single crystal, no observed in polycrystalline. And here it is rupture mode. So completely ductile fracture of crystals, very ductile metals like gold and lead neck down to a point and fade. Here technically there is no fracture. There is not enough material left to support the load. Another is ductile fracture. There is a neck formation here, and then finally cup and cone fracture is formed here after the neck. So ductile fracture of usually polycrystals, cup and cone fracture. Cracks may nucleate at the second phase particles or void deformation at the matrix particle interface. So these are some contributors who have been involved in uh, the evolution of fracture mechanics. So early days of the study of fracture by English, by Griffiths. So these people are the very known uh, beginners of fracture mechanics. So English stress-based criteria for crack growth, which is local case. Again, energy-based criteria for crack growth or global case, which is by Griffiths. So these are the reference of this their work. Sorry, I want to remove this. This is disturbing a lot. So crack grows and fracture. How can I minimize this? Initially, we try to understand crack propagation in brittle materials, where the crack are sharpened. There is very little crack tip plasticity. This is done in this is a domain of linear elastic fracture mechanics or LEFM. For the crack to propagate, the necessary global criterion according to Griffiths and the sufficient local criterion according to English have to be satisfied. The kind of loading or stress also matters. Tensile stress tend to open up crack, while the compressive stress tend to close the crack. So when we apply tensile loading, it tends to open the crack. And when we compress it in opposite direction, it tends to close the crack. So for crack growth to occur, it should be generally favorable. Sufficient stress concentration should exist at the crack tip to break bonds, and the crack growth criteria should be fulfilled. Crack growth criteria according to Griffiths, which is energy-based, or global criteria must be fulfilled, or according to English, that stress-based criteria or local criteria should be fulfilled. The stress-based criteria for crack propagation, that is English criteria. So in 1913, English observed the stress concentration around the hole or notch depended on the radius of curvature of the notch. That means the far field stress sigma naught is amplified near to the hole. Okay, that is sigma max over sigma naught is the stress concentration factor K. Flattened elliptical hole with a sharp tip can be thought of as a crack. So we can see here hole, circular hole, and when we see an elliptical notch, which is considered as a crack. Okay, even the whole circular hole also considered as a crack. So sigma max is equals to sigma naught as a whole plus 1 plus 2 radical of C over rho, which for sharp cracks, that sigma max is approximately equal to 2 times of sigma naught radical C over rho. So what sigma naught is far field stress, and sigma max is stress at hole or crack tip, and rho is hole or crack tip radius, and also C is the crack length or length of the hole or crack, and the K is the stress concentration factor. Stress concentration factor, okay. So whenever the crack is very sharp, sigma max is equal to 2 times of sigma naught over C. Sharper the crack, higher the stress concentration. That is, so this crack is sharper means we are saying that the radius of crack tip is very small. Rho, crack tip radius rho is very small. More stress amplification or higher value of sigma max will be attained. The circular hole has a stress concentration factor of 3, that is K is equals to 3. From English, okay, that means what? For circular crack, C and rho are equal. That means 1 over C over C, that is 1, radical 1, then it is 2 times of radical 1, gives us 2, 2 plus 1, 3. So we can see it here. Yeah. C over C for circular hole, rho and C are equal. So C over C, we can get this 1, 1 plus 1, 2, 3 times sigma naught. Sigma max equal to 3 times sigma naught. Once we, one way of understanding this formula is if sigma max exceeds sigma t, the theoretical fracture stress, then the material fades by extension of the crack. This is despite the fact that the applied stress is of much lower magnitude than the theoretical fracture stress. Yeah, so this is for circular hole. For the crack to propagate, the crack tip stress have to do work to break the bonds at the crack tip. This implies that the cohesive energy has to be overcome. If there is no plastic deformation or any other mechanisms of dissipation of energy, the work done appears as the surface energy of the crack surface. Okay, so the fracture stress sigma F, which is the far field of applied stress, can be computed using the approach. Not, so this is sigma cohesive, which is equals to E over pi, and the sigma F is equals to E gamma rho over 4A naught C. So this C is the length of crack. A naught is interatomic spacing or the distance between center of atoms. This implies the Young's modulus of material, and this is the radius of the crack. Okay. Now, how do the crack tip stress look like? Look, this is the cracked area. So around here there is a crack tip. So 30 millimeter by 10 millimeter size by zoomed out. Okay, we can see here plane strains condition. At the point near to the crack, at the crack tip, there is high stress, that is 8.9, that is high stress concentration. Once we go behind, we can see 3.5 gigapascal, sorry, and then 2 gigapascal and 1 gigapascal. In this region, we can observe 0.5, and this around here 0.2, and go far, it is 0. Here also we can see sigma xx. In the sigma xx also, as a near to crack tip 5.3 gigapascal, then around here 1.5 gigapascal, 0.8, 0.6, 0.4, 0.2, 0.1, and 0. So this is the stress distribution in plane stress condition. So Griffith's criteria for brittle crack propagation. We have noted that the crack length does not appear independently of the crack tip radius in English formula. Intuitively, we can feel that longer crack must be more deleterious. Another point um, northwards in English approach is the implicit assumptions that sufficient energy is available in the elastic body to do work to propagate the crack. Okay, so keeping some of these factors in view, Griffiths proposed a condition for crack propagation. Some of the conditions, the first one is bones of the crack tip must be stressed to point of failure, as in English criteria. The amount of strain energy released by the slight unloading of the body due to crack extension must be greater than or equal to surface energy of the crack face created. The second condition, this means the amount of strain energy released must be greater than or equal to surface energy of the crack face creating. This implies dUs over dc, the strain energy. This US implies strain energy over dc is a small increment in crack length. Okay, should be greater than or equal to du gamma over dc. This du gamma implies surface energy, or it is energy per unit area, which is surface energy. Essentially, this is like energy balance. The surface energy for the extended crack phase comes from elastically stored energy in a fixed displacement case. Okay. The strain energy released on introduction of very narrow elliptical double-ended crack of the length 2c in infinite plate widths or depths under an uniform stress sigma A is given by the formula reduction in elastic strain is equal to delta U, which is equal to U without crack minus U with crack. So which is equal to US. US is equal to pi C square sigma A square over E. And should be written with negative sign when we reverse the direction, if it is U final minus U initial. Okay. So this is because the body with a crack has lower elastic energy stored in it is compared to the body without crack. Also, the assumption is the introduction of the crack does not alter the far field stress. Okay, we can see here what the far field stress. Here, this is load applying. The far field stress are sigma y, which is equal to sigma y, which is equal to sigma a. For now, we assume the stress, this stress arise out of applied displacement are this sigma yy, and this is double-ended through crack, with 2c. Okay, so these are the crack phase. So the unit of US is joule per meter, which is takes the unit of energy. Half crack length is C appears in the formula. E is assumed constant in the process. Sigma is the far field stress. This may result from displacement rather than from the applied force. So the formula for US can be appreciated by considering the energy release from the circular regions of diameter 2c as in the figure. The energy releases, which is given elastic energy release from circular region US circular, which is equal to half sigma A square over E times pi c square. That is, this is for the fully circular region. Okay, so the computation of the actual energy release is more involved and is given by the formula US is equal to pi c square sigma a square over E. So plane stress condition. This is in plane stress condition. Hence, duc dus over dc, which is equal to 2 pi c sigma a square over E. So here, in this case, energy release from the circular region is given by the formula 1 here as above. So that is taken for this region. Okay. For the body in plane strain condition, thickness in z direction into the plane of the page, E is replaced with E over 1 minus mu square. So US is equals to the strain energy. US is equals to pi c square sigma A over E times 1 minus E over 1 minus mu. That is plane strain condition. As plane strain is more severe on the material, it is better to experiment in the plane strain condition. The surface energy of the crack length 2c and the unit width over depth is fracture surface energy U is equals to 4 gamma fc. And from this, du of gamma over dc is equals to 4 gamma f. This is the difference in the energy between body with crack and one without crack. As pointed out before, the surface energy is the fracture surface energy and not just the surface free energy. The origin of this energy is contributions from the dissipative mechanisms like plastic deformation, micro cracking, and phase transformation, in addition to the energy of the broken bonds. The unit of joule per meter depth of the body is applicable. Note that the Griffiths experiment is easily understood in the displacement controlled mode, that is applying a constant displacement and see what happened to the crack. And it is more difficult to comprehend it in the force control mode by applying constant far field force. In the force control mode, the force do work on the system and hence the energy accounting process is more involved. Therefore, it is better to visualize sigma as arising from far field applied displacement. Okay, so now we have formula for US and the U gamma, which are required. So, and we already formulated this. From this, we obtain this formula. Okay. So, combining these two formulas together, this one dus over dc is this formula, and du gamma over dc is this one, which is given here. So from the two, the left-hand side increase linearly with c, while right-hand side is constant. Okay, so this one is increase with c. As c increase, as the crack length increase, this will increase, and this one is constant. The equal representation, the bare minimum requirement, the critical condition. That means the minimum crack size, which will propagate with a balance in energy. That is in between the elastic energy release due to crack extension and the penalty in terms of the fracture surface energy. So the critical crack size is calculated from this relation. So C critical, which is equals to cross in this equation, we can find 2e gamma f over pi sigma a square. C is the half crack length. As we know, it is 2c, so it is half crack length. A crack below this critical size will not propagate under the constant stress sigma A. Whether a crack of size greater than or equal to C strike will propagate will depend on the English condition begin being satisfied at the crack tip. A sufficient stress concentration should exist. This stress sigma A now become the fracture stress sigma F. Crack of the length C strike will grow unstably if the stress exceeds sigma F. So C strike is equal to 2 times of gamma F over phi sigma F square. That is according to Griff's criteria. This criteria finally what you can get this crack propagation just starts to pi c sigma a square over e is equal to 4 gamma f. Substituting the strike condition here, finally what we can get is this formula. Okay, so C is equals to 2e gamma f pi sigma f square is the thing which we need critically now. So the Griffiths formula sigma f is equals to radical of 2 gamma e over pi c. For that, at a constant c, that is c is equals to c critical, when sigma exceeds sigma f, then the specimen fails. That means sigma f, the failure stress sigma f is equals to radical of 2 gamma e over pi c 1 minus the Poisson ratio of material mu square. An alternative way of understanding the Griffiths criteria, that is energy-based criteria, is here sigma naught, the far field stress. And once this happens, there is a small crack propagate. Change in energy on the introduction of the crack, delta U is equal to 4 RF, gamma FC minus pi c square sigma A square over E. This change in energy delta U should be negative with an increase in crack. Look here, d delta U over dc is 0 at this point. Look, it is 0 here. Here it is positive slope. It shows positive slope. And then here it shows a negative slope. Okay, it shows negative slope. In the positive slope region, it is having a stable crack. But in the negative slope region, it has unstable cracks. At the point where d delta U over dc, which is a critical point of critical size of crack, it implies the critical size of crack that is 0. Yeah, so this is the representation for the equations of this thing. So Griffiths versus English criteria. For very sharp cracks, the availability of elastic energy near the crack tip will determine if the crack will grow. On the other hand, if available energy is sufficient, then the sharpness of the crack tip will determine if the crack will grow. Sharp crack is limited by availability of energy, while a blunt crack is limited by stress concentration. So for that, according to Griffiths, sigma F the fracture stress, which is equals to radical of 2 gamma E over pi c critical. And here, sigma f according to English, which is equals to E gamma rho over 4 A naught C. If rho is equals to 8A over pi, Griffiths and English criteria give the same result. If gamma is approximately equal to 3 times A naught, Griffiths and English criteria give the same result. The other crossover criteria, that is. So C strike, which is the critical crack length, is equals to 2 gamma E pi sigma F square. And according to English, it is E gamma over 4A naught sigma F square as a whole rho, that is radius or the crack radius. So modern fracture mechanics, stress intensity factor K, material parameter fracture toughness Kc, energy release rate G, material parameter in this case critical energy release rate Gc, J integral J, material parameter Jc, crack tip orientation, crack tip opening displacement, which is delta, material parameter delta C. So, so we are going to see another phenomena which is developed by Irwin, another scientist, G.R. Irwin, fracture dynamics. So we are going to see that point. Historically, in the old times, sorry, I'm going to just so now I'm going to see the concept of fracture mechanics. So historically, in 1910 to 20, fracture was studied using English and Griffiths. These are two scientists who began the fracture mechanics, and they are called fathers of fracture mechanics. Wherein the fracture stress sigma f was calculated either using global or local criteria. So the birth of fracture mechanics is 1990s. About 1990s, more scientists appeared and developed the fracture mechanics to framework to the current state, and lead to the concept of stress intensity factor K, energy release rate G, by Irwins and other scientists. This concept worked well in the domain of linear fracture mechanics or linear elastic fracture mechanics for breathing materials. Crack tip stress were characterized by the stress intensity factor. In the presence of crack tip plasticity, some of these concepts were extended if the crack tip plasticity was small or very small scale yielding. In ductile materials with the large plastic deformation at the crack tip, concept of J integral is evolved, wherein the stress fields ahead of the crack tip are termed as HRR fields, and the J integral characteristic characterize the field intensity of the crack tip. The concept of crack tip opening displacement CTOD was also proposed to characterize the cracks in ductile material. So concept of energy release rate, or G. G is defined as the total potential energy, pi, decreasing during unit crack extension. That DC means a small change in crack length. G is also referred to as a crack extension for force, and is given by G is equal to d pi over dc, with the minus sign. Okay, so that pi is the total potential energy. The potential energy is difficult quantity to visualize. In the absence of external traction, that means we are applying the displacement controlled loading condition or boundary condition. So if there is no load or traction, it is difficult to visualize. The potential energy is equal to the strain energy stored in state. So in our case, the pi equal to US. So we can substitute that US instead of pi. So G is equals to dUS over dC minus of. With the displacement boundary condition, only G has unit of joule per meter square or Newton per meter. So as we have seen, US is given by US is equal to pi c square sigma square over E. Therefore, G is equals to 2 pi c. Integrating this U with DC, we can get 2 pi c sigma A square over E. Crack growth occur if G exceeds a critical value GC. GC is the critical value of energy release rate, which is the fracture toughness of the material. So G is equal to GC for perfectly brittle solids, or GC is equal to 2 times gamma F. This equivalent to Griff's criteria. Okay. So it is better to understand the basic of fracture with fixed displacement boundary condition without any surface traction. So a relation between K and the G. In spite of the fact that G has more direct physical interpretation for the crack growth process, usually we work with K as it is more amenable to theoretical competition. K can be related with G by the following formula. So K is equals to GE for the plane stress condition, and for the plane strain condition, K square is equals to GE over 1 minus mu square, because in plane strain, the instead of E we have E over 1 over, yeah, let me write it. Okay, screen pointer, okay, okay. So E is equals to, instead of E we use E over, okay, I can say 1 minus mu square. So because of that, this is substituted with this value for plane strain case. Okay, the stress fields at the crack tips. For the body subjected for far field biaxial stress. Look, here there is biaxial stress. Okay, stress in the Y, stress in the X. And there is a crack here with a double ended through crack, 2C. Okay, so for the body subject to biaxial stress, sigma naught with double ended crack of length 2C, the stress state is given as for mode 1 loading. Actually, this is for mode 1 loading. Sigma XX is equals to K1 over radical of 2 pi r. Cos theta over 2 times 1 minus sine theta over 2 times sine 3 theta over 2. This is taken as equation number 1. For yy, the same equation also holds true. And for xy, that is for the shear case, we have only, actually not the same, sigma yy has 1 plus sine theta over 2 here. Here 1 minus sine theta over 2, that is the difference. And here, instead of this 1 minus or 1 plus, it is simply sine theta over 2. These three formulas are there. So sigma ij is proportional is 1 over radical of r. Okay, so the inverse square root of r, that is singularity at the crack tip. The intensity of the singularity is captured by Ki, the stress intensity factor. This Ki is stress intensity factor, or Ki is the scaling factor for the singularity. This is the meaning of Ki. As no material can withstand infinite stress, inductile material plastically will intervene. Clearly, the solutions are not valid exactly at the very near to the crack tip. At theta is equal to 0 and r approach to infinity, the stress sigma xs and yy should tend to sigma naught, because here k1 is there. When gamma, this r approach to infinity, and the theta 0. Theta 0 means cos 0 is 1. 1 minus sine 0. Sine 0 is 0. This sine 0 is 0. This part will get 0. So 1 times 1, 1. So k1 over, we have left k1 over 2 pi r cos 0. So cos 0 times 1, we can get 1. So we have left k over this thing. Here also the same. This part will get 0. Okay. This part will get 0. This is 1. This is 1. And gamma approach to infinity means k over infinity. Means just 1 over infinity means it is almost 1. So finally, what that sigma naught? This is not the case, as seen from the equation 1 and the 2. This implies that the equation should be used only close to the crack tip, with little error, or additional terms must be added to the equation. Okay. So understand the stress field equation. So this sigma xx, the stress field equation, sigma xx is ki over 2 pi r cos theta over 2, 1 minus sine theta over 2, sine 3 theta over 2, which implies sigma xx is equal to k1, taking this as a function of theta. This quantities as a function of theta. So f of theta over radical of 2 pi r. Again, this is also a function of r. So we can put it as f of r theta. Okay, so sigma x is equal to ki f of r theta in terms of function. So this ki indicates mode 1 loading. Okay, and the y is shape factor. The shape factor related to geometry. And sigma naught is the stress, or the far field stress, and pi c is the half crack length. So this is the relation for ki. So ki is equals to y times sigma naught radical pi c. Okay, so ki is the strength and intensity factor, or quantifies the magnitude of the effect of stress singularity at the crack tip, according to as given in the Antonio C. Fisher Creep Introduction to Contact Mechanics, Springer 2007, and that K has unit of Newton per meter square. That is stress Newton per meter square times radical of meter, or Pascal per Pascal radical meter. Typically it is megapascal radical meter or Pascal radical meter. So quadrupling the crack length is equivalent to doubling the stress applied. Hence, K captures the combined effect of crack length and loading. The remaining part in equation 2 is purely the location of the point in r and theta, that in the coordinate. Note that there is no crack tip radius rho in the equation. The assumption used in the derivation of equation 1 to 3 are rho is equal to 0, infinite body, biaxial loading. The factor y is considered in the next page. So that shape factor y, okay, so how we can, it's obvious that geometry of the crack and its relation to the body will play an important role on the effect on the fracture. The factor y depends on the geometry of specimen with the crack. Y is equal to 1 implies for the body considered in figure 1. This is the figure. In this case, y is equals to 1. Regions for where additional strain energy is released, these are okay, double-ended cracks in infinite body. Y is equal to 1.12 for the surface crack. The values of y is greater than by 12% for the surface crack as additional strain. Y is equals to 2 over pi for embedded penny-shaped crack, and y is equal to 0.713 for the surface half penny cracks. Region of K dominance. The crack tip field consists of two parts. One is singular part, which blow up near the crack tip, and the second is the non-singular part. The region near the crack tip, where the singular part can describe the stress field, is the K dominant region. This is the region where the stress intensity factor can be used to characterize the crack tip stress field. In material, where the crack tip plasticized zone is smaller, then the K dominant region also called the small scale linear, that is SSY region. Concepts of the linear elastic fracture mechanics can be used with the little error. Fracture toughness, that is Irwin's K-based. One of an important goal of fracture mechanics is to derive the material parameter, which characterize cracks in the material. This will be a key to yield stress sigma in the uniaxial tension test. Sigma y is the critical value of stress, which if exceeds sigma greater than sigma y, then yielding occur. The criterion or critical condition for fracture in mode 1 can be written as K1 is equals to KIC. This is critical fracture toughness, where Ki is the critical values of stress intensity factor, and known as fracture toughness. Okay, this K1I is a fracture toughness. K1C is the material property, like yield stress, and can be determined by the different materials using standard testing methods. K1 is a microstructural sensitive property. The focus here is local crack tip regions and not global. As the case of Griffith's approach, all the restrictions or assumptions on K will apply to K1C, Okay, that materials are linear elastic behavior. That means no plastic deformation or other non-linear behaviors. Inverse square root singularity exists at the crack tip, and the K-dominant regions characterize the crack effect. So sigma xx is equal to Ki over f of theta over radical to 2 pi r. Fracture toughness K1C for some typical materials. For cast iron, it is 32, 33. For low carbon steel, 77. For stainless steel, 220. For aluminum alloy, 220, 24 T3, that is 33. Aluminum alloy of 70, 75. T6, 28. For titanium aluminum alloy type, Ti6Al4V55, inconel alloys of 600 or nickel-based alloy, it is 110. So we have already noted the fracture toughness is a microstructure sensitive property, and hence to get true values, the microstructure has to be specified. So this is referred from fracture mechanics, CT Sun and ZH Journal, academic press Oxford to 2012. So these values are taken from there. Is KIC really the material property like sigma y? Let's see what. So ideally, we would like to like KIC in mode 1 loading, and the K2C and the K3C will be the corresponding material property under other modes of the second third mode to be material property, independent of the geometry of the specimen. In reality, KIC depends on the specimen geometry and the loading conditions. The value of KIC is especially sensitive to the thickness of the material. Thickness, a thick specimen represents a state that is closer to the plane strain condition, which tends to suppress the plastic deformation and hence promotes the crack growth. And the experimental determination value of K1C will be lower for the body in the plane strain condition. On the other hand, if the specimen is thin, means the thickness is very small, okay, plastic deformation can take place and hence the measured K1C will be higher. In this case, if the extent of plastic deformation is larger than K1, will no longer be a parameter which characterize the crack tip accuracy. So here, thickness T of material also another factor. Okay. To use K1C as a design parameter, we have to use its conservative values. Means the minimum thickness is prescribed in the standard sample for the determination of fracture toughness. This implies that KIC is the value determined from plane strain tests. How do I understand the fracture criteria? First, one has to decide if the material is brittle or ductile. That is the first phase. If the crack tip is sharp or blunt. Okay, for the brittle it is sharp, for the ductile it is blunt. If the material is brittle, one has to decide the material is linearly elastic or not. Again, another, whether it is linearly elastic or not is another case. For the linear elastic material, we can apply the concept of K and the material property Kc. Usually in the mode 1, this quantity become K1 and K1C. We would also use G and GC, that is fracture energy. If the material is ductile, then we need to determine if the plastic zone is small compared to the K dominant zone. If yes, then we can continue to use the concept of K and the G. If the crack tip plasticity is larger, then we have to use the concept of the like J integral and CTOD or that delta function. The crack tip stress field in the case is given by the HRR fields, noting that technical JC is for the crack nucleation. Essentially, there are two approaches: global and local approach. Global is in the energy base, and local is in the stress base, according to the English and these two scientists based on their work. For the linear elastic material, the energy and the stress field approach can be considered equivalent. Okay, so what is ductile fractures? In ductile materials, crack tip stress lead to plastic deformation at the crack tip, which further leads to crack tip blunting. Energy is consumed due to plastic deformation at the crack tip, which comes from elastic strain energy. This implies less energy is available for crack growth. Crack tip blunting leads to reduced stress amplification as the crack tip. Blunting will avoid stress singularity at the crack tip and may lead to maximum stress at certain distance from the crack tip. Okay, so crack tip blunting will lead to an increased resistance to crack propagation and increased fracture toughness. So we can see here here sigma yy for sharp crack tips. This is sharp crack tip, as we see. As we increase the crack length, the stress decrease and comes to down, which is a function of 1 over radical of R. When we come to here, maximum stress little ahead of the crack tip. This is the blunt tip. So it is not at here, it is just somewhere here. This is the point where the maximum stress is, which is just ahead of the crack. So crack is here and the maximum is occurred here. And the graph shows the blunted crack. So this is a schematic stress plot for blunted cracks and for the sharp cracks. Crack propagation in ductile material. In brittle material, the maximum crack opening stress or mode 1 is the crack tip ends, and hence crack propagation involves breaking of the bond at the crack tip. Sorry. So ductile material, I'll come back just for 1 minute. So in ductile material, the maximum of stress lies a little ahead of the crack tip, as we have discussed. So it is here. Okay, it is ahead of a crack tip. Crack tip is here. Here it is a blunt crack, and we can observe stress ahead of the crack. Okay, so in this scenario, the mechanism of crack changes. Okay, so void nucleate in the region of the high stress region, as so when we come here, it nucleates some void here on the regions of the maximum stress. So here we can observe void nucleation. Okay, so formation of void in the region of high tensile stress. Okay, the region between the void and the crack tip acts like a tensile specimen and the microvoid formed in this region. Okay, so we can see in the region around here we can observe microvoids. These are microvoids, formation of microvoids due to the formation of void in the region of high tensile stress. And crack extension occurs by the coalescence of the mic. So here we can see the coalescence of microvoids leading to the extension of the crack. So this is the coalescence of microvoids. So that leads to high crack in the material. What happened to a crack in the ductile material? So high magnitude of crack tip stress can cause yielding as a crack tip, plastic deforming that is. This leads to crack tip blunting, which reduces the stress amplification. There develops a zone ahead of the crack tip known as a processor. What else can happen at the crack tip due to high stress? High magnitudes of crack tip stress can cause a phase transmission, that is tetragonal to monoclinic phase in the Y3 stabilized zirconia. So this is all about the first phase of our presentation. I will continue with some second phase of presentation. So that will be also continued. So let's see what the fracture toughness means. So it is better to stop here. I'll continue the remaining lecture in the next class. Thank you very much for paying attention. Thank you.